Hello, ladies and gentlemen. Today we're going to be talking about imaginary numbers, also otherwise known as complex numbers. Basically, you should have kind of gone through that discovery activity and seen where these numbers kind of come from, all right? So for a long time, we've been telling you all that, hey, you cannot do the square root of a negative. Square root of a negative is not real. It doesn't exist. You can't do it. And while that is true, it is not real. It doesn't mean that it doesn't exist in some sense. It's actually what we call an imaginary number, okay? So basically what happened is that back in the day, mathematicians were trying to solve some really complicated problems, and they noticed that if they used these numbers, these complex numbers, they were actually able to solve these more complicated problems. Even though they were using these numbers that weren't real, it would end up turning into numbers that were real, okay? So it kind of was this kind of weird, well, we use these numbers and are real, but it made us get this real answer we were looking for, okay? And that's kind of where complex numbers came from. And we'll see them a lot with quadratics because we're square rooting things, they kind of show up all the time, okay? A lot of our quadratic formula problems will end up with an imaginary root or complex roots, okay? So basically, not all quadratic equations are going to have real answers. For example, x squared equals -1 does not have a real answer. So what we did was we decided to kind of come up with a fake answer that we can then use to solve that. And what we do is basically the square root of -1 we now define as I, okay? So I've said before, don't ever use I as a variable because we actually have a very specific meaning for it. It means the square root of -1. It's also called the imaginary unit, okay? It's the imaginary unit, the square root of -1. Now, there's a couple cool things we can actually do with I and the square root of -1. For example, if you square it, I squared will actually equal -1. Now, if you think about why is that the case, because if I square the square root of -1, I'll end up getting what's on the inside, right? Or if you square square root, I square -1, I square it. If you square square root, those cancel, and you get whatever's on the inside, which in this case is -1, a real number. So squaring this imaginary number, I actually get a real number, which is pretty cool, okay? So that's kind of some of the cool things about this I that we have. The way that we're going to write numbers that are imaginary is that we're going to be pulling out the negative from the square root and writing it on the outside as I. So for example, if I have the square root of -r, I take this -1, pull it out, and I say I square root of r. So the square root of -5, this actually should just be a 5 here, so ignore this negative there. It's a typo. But it should be I square root of 5. Okay, so basically we can pull that out and pull it out to the outside. If I square it by using this property up here, it actually would just be the opposite of whatever's on the inside. So if I had I square root of 5 squared, it would end up being just -5. Okay, so kind of how we're going to rewrite all these things and how we're going to do that. All right, so for example, the square root of -1, that's going to be I. If we had the square root of -7, we could rewrite that as the square root of -1 times the square root of 7. The square root of -1 we know is I, so it would be I square root of 7. Okay? The square root of -16, we could split that into the square root of -1 times the square root of 16. And we know that the square root of 16 is 4. And we know this is I, so we can rewrite that as 4I, or I times 4. It kind of looks like a variable. We kind of almost treat it like a variable, like, oh, it has a coefficient and a letter. But we already know that letter has a defined meaning. It's not actually a variable where it's like, hey, I can plug anything I want into that letter. It is the square root of -1. We're just rewriting it, okay? This one down here, the square root of -24, I can rewrite that as the square root of -1 times the square root of 24. I know that the square root of -1 is I. The square root of 24 I can simplify and say, oh, that's 4 times 6. And so I end up with 2I, the square root of 6. Okay, go ahead and I pull that out and I do that, okay? Now, we're going to kind of do a little bit of a thought exercise. I'm going to kind of scroll down here to where I have some blank space. We're going to kind of think about these I's and how they relate again. So, once again, I, we know is equal to the square root of -1, okay? And it's kind of an italicized I try to use when I write it, all right? We just said that I squared is, in fact, -1 because it would be the square root of -1 squared, which will be -1, okay? We can kind of keep going. Let's see if we can do I to the third, okay? So I to the third, we know that I to the third, well, if I think about my exponent laws and some of the exponent laws I have, that's equal to I squared times I. And as we just said, I squared is -1, so this is kind of equal to negative I, right? Which is the negative square root of -1. But just for the sake of what we're doing, we'll say that's negative I. If I have I to the 4th, well, I could rewrite that as I squared times I squared, which we know is -1 times -1, so that's going to equal 1. If I go to do I to the 5th, we're just going to keep going. We're going to keep going, keep listing these exponents, keep going as far as we can. I to the 5th, well, what can I rewrite that as? Well, maybe I could rewrite that as I to the 4th times I. And as we just said, I to the 4th is 1, so 1 times I, that's just going to equal I. The next one, I to the 6th, well, if we think about it, that's going to be I to the 4th times I squared. And again, I to the 4th is 1, so I can see I squared, that was -1, so that's going to equal -1. If I go and I do I to the 7th, again, that's going to be I to the 4th times I to the 3rd, which we said I to the 3rd was equal to -I, so this is going to equal -I. And then if I go to do I to the 8th, that's just I to the 4th times I to the 4th, which will equal 1. Now, you might start to be noticing a pattern. Let's try to think about it. What if I just write I to the 9th and I say, hey, I don't want to think about any of this other stuff. What's I to the 9th going to equal? I'm going to tell you right now it's going to equal I. And then if you go to do I to the 10th, without even doing any math or thinking about it, I'm going to tell you that that's going to equal -1. And if you do I to the 11th, without doing any math or thinking about it, I'm going to tell you that that equals -I. And if you do I to the 12th, without doing any math or thinking about it, I'm going to tell you that that equals 1. This pattern is going to repeat itself over and over again based off the way that these exponents behave. I'm going to get I, -1, -I, 1. I, -1, -I, 1. I, -1, -I, 1. In fact, I can give you I to any old crazy power, any power I want to, and you can actually tell me what it equals based off of this pattern. So for example, I can say, hey, let's do I to the 397th, and let's figure out what that equals, okay? Well, here's the thing. I don't want to list out this pattern 397 times. Okay, well, the next one will be I, then we're going to have -1, and then we're going to have -I, and then we're going to have 1, and just keep going. I don't want to list that out, okay? We actually can figure out what step of the pattern we're on by doing a little bit of critical thinking, okay? So we have 4 steps to our pattern here, okay? This is step 1, this is step 2, this is step 3, and this is step 4, okay? What's cool about that is that these numbers are all divisible by 4. So here, we're going to make these numbers, we're going to divide by 4 to figure out what step of the pattern we're on. So here's how we do that. We're going to take 397 and we're going to divide it by 4. So here, I'm going to grab my handy calculator. Okay, I got my calculator. I'm going to say, all right, 397 divided by 4. Now, when I do that, I'm going to get some crazy number. In this case, let's hold up the camera. I got 99.25. Now, I could sit there and be like, 99.25, what the heck does that mean? The 99, the number that you get, means nothing. We don't care about that number. What we care about is the decimal, because the decimal is actually telling you your remainder. We divided by 4, so this decimal, 0.25, is telling us 1 out of 4, right? 0.25 is 1 out of 4. That's actually telling you what step of the pattern you are on. If you get 0.25, you are on step 1. If you get 0.5, you are on step 2. If you get 0.75, you're on step 3. And if you get 0, you're on step 4 out of 4. 1 out of 4, 2 out of 4, 3 out of 4, 4 out of 4. So because we got 1 out of 4, I know that I to the 397th is going to equal my step 1, which is just I. Okay? So we can simplify these really big exponents, or i's as really big exponents, just by using that fact right there. Okay, so pretty cool. Divided by 4, you can figure out what I you're on. Okay, all right, a little bit of a tangent. Let's keep kind of moving on a little bit. The next thing I want to talk about is complex numbers written in a standard form. So Here's kind of the deal, guys. Forever, remember, I don't know if you remember this, but at some point a math teacher told you, hey, by the way, every number secretly has a decimal, right? So 4 is secretly 4.0. There's always a decimal hiding there. Well, I'm going to kind of blow your minds again and say, hey, guys, every number you've ever talked about secretly has an imaginary component to it as well. So these numbers, complex numbers, are basically the way that we write numbers when we want to kind of call out that there's an imaginary component to every number, okay? So the two kind of numbers you can have when we're talking about complex numbers, you either have your real numbers, okay? Those are the ones that we've been dealing with our whole lives. So -1, 3, 5 halves, √2, pi. Those are all real numbers. They secretly have a plus 0i hiding with them. We don't really ever write it out because it doesn't really mean anything. We don't really need to worry about it, but it's secretly there, okay? They have where that imaginary component is 0, okay? Imaginary numbers or complex numbers, those numbers have something with that I. They have some sort of imaginary component to them. So for example, 2 plus 3i, that would be an imaginary number. 5 minus 5i, that would be an imaginary number. Okay, and then we even have pure imaginary numbers, which are a smaller subset. Those ones have no real component. They're only imaginary. So -4i, 6i, things like that. Okay, so this diagram right here kind of shows you the different complex numbers, the complex number system. We either have real numbers where they don't have an imaginary component, imaginary numbers that have an imaginary component, and then more specifically these pure numbers that don't have any real component at all, only have that imaginary portion to them. Okay, so those are kind of our imaginary numbers. Okay. The one thing today I'm going to really be asking you to do is you're going to need to be able to write out some imaginary numbers for me. So for example, I might say, hey, here's the square root of -8. What would that be as an imaginary number? And you'd say, oh, well, -1, right, goes into that. So I know it's going to be the square root of -1 times 4 times 2. And then just like when you simplify square roots, we pull out these -1s. So this is going to be I 2 root 2. Or you can say 2i root 2 or 2 root 2i. Doesn't matter kind of where you put the I, okay? For this one here, write this as we can. I squared, we can go down to our big old list we made down here, but we know I squared equals -1. So really what this problem is just -12 minus 2. So we can rewrite this one as -14. If I wanted to write it as a complex number, I could say it's -14 plus 0i. Okay, because there's always secretly that imaginary component hiding with it. This one over here, we have the square root of 9 plus square root of -48. The square root of 9 I know is equal to 3. -48, I can start simplifying it by saying, okay, what does this break down to? Well, it's going to be -1. It's going to be times, let's see, what goes into 48? We can have 16 times 3. That's what I was looking for. Okay, and then we know that the square root of 16 is 4. We know that square root of -1 is I. So we'd say 3 plus 4i square root of 3. Okay, and that would be our number listed as a complex number. Okay, so that's kind of an introduction to imaginary numbers and complex numbers. Tomorrow we're going to kind of get into how to do some operations with them, but that's sort of our just kind of introduction to what they are. Thank you all for watching.